All right, this is my Lab 4 presentation for spring oscillation movement. For my table of contents, I have my introduction, my data observations and models, my code, my discussion, and then my conclusion. So for the introduction, the purpose and fundamental principles here. The purpose of this lab is to see how energy changes through an oscillating spring and mass system and plot these changes to compare the motion of the object. The fundamental principles at play here are the momentum principle and the energy principle. In a preview of the results, the position changes for the spring were found, and then the oscillation period could be calculated from the positional data. So Newton's second law and the energy principle are two important concepts to understand. Newton's second law, known as the momentum principle, states that a force is equal to the change of momentum over the change of time, and it indicates the changes of movement within the systems and the surroundings. The energy principle is the idea that total energy of a system is equal to the work done by the surroundings plus the energy change from heat. So for the procedure, an example video of the mass oscillating on the spring was used, and then the tracker program was used to define center of mass calibration sticks and axes to properly record the motion of the mass, and then tracker data was used to find a diagram of the spring mass model. So for tracker data and initial conditions, we have our initial position being negative 0.113 and then negative 0.632 meters. The velocity was 0, the mass was 0.4 grams. Our L null was 0.127, our start time was 0 seconds. And the system and the surroundings, the system was the spring and the mass, and the surroundings were gravity. So for what was changed, the mass was changed for the code to set it equal to the mass that we used, and then the energy formulas, the net force formulas, the position update, velocity update, and final energy formulas were all changed. And all of these were used in order to record the changes in the energy of the spring throughout its oscillating movement to see how the total energy of the system was impacted. So for the diagrams, we can see that it displays the components of the net force broken up into its separate forces, which is the spring force and the force due to gravity. Force due to gravity is always down, and the spring force will all point either towards or away from the origin of the spring, depending on whether it is compressed or relaxed. So the results, you can see that gravitational potential energy and potential spring energy pretty much always were equal and opposite to each other, while kinetic energy fluctuated while those were lower. At potential energy peak, kinetic energy was equal to 0, and the overall energy of the system was equal to 0. So as far as the comparisons, blue line shows the computational model, the red line is observed position changes. They were both very, very similar with some slight fluctuations, but this makes sense considering that there are other factors at play when you're doing an experimental model, like wind resistance, drag, acceleration, that are nullified in a computer model. So for conclusions, what does it mean? So the energy principle is satisfied here since the overall energy is just transferred from one to another and work is not done in the system. So therefore the total energy equals 0, and this makes sense since gravitational potential energy and potential spring energy are always canceling each other out, and kinetic energy will make up the extra fluctuation that's necessary when they do not fully cancel each other out. So the total energy is consistently 0 throughout the entire motion of the spring and mass. And then the estimations for the oscillation period found by taking the farthest x value negative and positive, and then the farthest y value negative and positive, and then finding the time it took to go in a complete cycle, meant the x was 1.7 seconds and the y was 1.55 seconds.